Okay, welcome back from lunch. Um, I show this image again, like I did yesterday, and now you might think, well, why the hell did Seb show this image yesterday? He really didn't talk about these meso to submesoscale features, because we focused a lot on the mixed layer dynamics. And today I really hope I'm going to try and give you as best our sense of what we know in the Southern Ocean and what observations we have from the Southern Ocean, how these are scaling together from the mesoscale at the 30 kilometer down to the 3 kilometer or even smaller. This guy. All right, so yesterday we kind of covered this. I'm not going to talk about really the mixed layer itself, although much I'm going to be explaining today is that there are these horizontal circulations, these submesoscale flows that are mostly found in the mixed layer. And there's a caveat there because, we're really at a frontier of our understanding about how these circulations can exist also outside of the mixed layer, or at least reach outside of the mixed layer, whether it's on the surface boundary layer or the bottom mixed layer, which we didn't talk about yesterday. And again, I'm going to try and give some examples splattered throughout of these, how these processes really affect the top mixed layer fluxes, air sea fluxes, and the bottom boundary ventilation from some examples that have come out of the Southern Ocean of recent, not necessarily of work that I've done, but of the community. Okay, so yeah, we looked at this yesterday. We have these poor constraints of this mixed layer in the Southern Ocean. The fine scale view of the Southern Ocean, when you start increasing the frequency of the resolution, means that we have these large adjustments in these mixed layer depths from 30 odd meters to 300 odd meters. And we only really looked at a 1D view of that yesterday. But if you were to kind of blow up this image to the 3-dimension or even the 2-dimension, kind of like what you have here on the bottom panel, you can see that this kind of one-dimensional view is set within an inhomogeneous field of gradients in the ocean that extend from the mesoscale, those that are balanced by the Coriolis force of the Earth, to those that are unbalanced, very small filaments and small submesoscale eddies. And this is a simulation which I really like to use here. Some work done by Uchida and also Sarah Nicholson, who kind of in parallel did these studies independently of looking at how the Southern Ocean impacts in this case, the flux of the micronutrient iron to the surface layer of the ocean. So this is effectively seen as a kind of a iron concentration or a response of phytoplankton growth in the surface layer from iron availability. And what you can see is they are acting as this wonderful tracer in the model of all these flows that occur at various scales, various horizontal scales. And of course, you can think of how this is embedded in the vertical scale, which you kind of can't see here on this projector, of this mixed layer that's modulated in this 3-dimensional circulation. And so just to give you a real sense of the horizontal scales of variability and where we are in our, let's say, modern terms of knowledge about this, well, here we have, in terms of the climate scale, we use all our CMIP simulations, and these are occurring at this scale. This is the current CMIP 6 that we can run at this resolution in our climate models. These are some examples from RNA Bierstosh, and I'm sorry, we're on the edge of the Southern Ocean here, but I love to use this Agulhas current as a good example, and I think David did this morning as well. And you can sort of see, okay, we have a current there. The next generation of models, the sort of 5-kilometer resolution, are now starting to really resolve the mesoscale really well. So there's a 5-kilometer grid spacing. That means that if you want to resolve an eddy of 30 or 50 kilometers, you've got just several points in the model that can actually start to resolve the flow dynamics of that model. And then beyond the climate models, and this was the problem I was talking about yesterday in Moore's law, is that this is beyond us to start resolving at, let's say, the 1-kilometer scale, the submesoscale. Which you can see here is this blended mix of the fine-scale ocean where these mesoscales are creating a lot of strain in the ocean and feeding these smaller instabilities called the submesoscale. So that's just to give you a context of like where we are in terms of our climate understanding at the global climate scale, and how it might change from our CMIP simulations and into comparisons. I like to bring up this Richardson's poem. It's now 101 years old. Big whirls have little whirls which feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. So it's a really nice quote by Richardson, and hopefully you can think about this at the end of the lecture today and how this kind of all fits into place, and you kind of see a little bit of this trajectory from that quote in these simulations. But let's go to some observations for the Southern Ocean. Okay, so here we go. We're leaving on a ship from Cape Town, and we're heading down, and we're dropping off these gliders and these USVs, these surface vehicles. In particular, I want to highlight this project we did in the marginal ice zone in about 2017-18. It was my first project after I moved to Sweden, so it was like, oof, got to use my money very carefully here. And what we did is we invested in these autonomous platforms. So here is a sailboy. So those of you who don't know what a sailboy, yesterday we kind of showed some of the wave glider data, and the sailboy is similarly a kind of surface platform that's using the wind to sail around like a sailboat. And all we do is we change the direction of the sailing boat in accordance to the wind direction so that it can tack in the wind and move around the ocean for us while collecting observations of the atmosphere and of the surface gradients of temperature and salinity. And then we put gliders, like the sea glider, we put them underneath these USVs so that we actually provide this coupled view of the surface boundary layer, like Sarah was talking about this morning, the air sea fluxes, the surface properties, and the subsurface sort of towards the interior of the ocean observations all simultaneously. Here's the sailboy doing its thing. So we're at about 60 south here in the Weddell Sea, and we told it to complete this transect of about 100 kilometers for 4 months. And we said, you just do your thing, stay within this corridor, make sure you use the winds appropriately to sail around and collect observations for us. And it did incredibly well. We didn't really know how a sailboy would work in the strong westerly wind belt of the Southern Ocean, but it stayed within this, tacking away. And you can see the color here is the wind speed that it's experiencing, and it's like trying to get back to its southern point and collect data along the way. Here's what the sailboy really experiences. This turbulent surface layer of the ocean, and like compared to what Sarah said, this is an extremely challenging place to collect observations, the marine boundary layer and the surface ocean. And here's the sailboy, which is a Norwegian-built autonomous platform, riding through these terrible conditions of the polar oceans. But they still collect really very nice observations. And here I just want to show you a simple time series of temperature and salinity collected from that autonomous sailing boat in the marginal ice zone of the Weddell Sea. So we have things like salinity and temperature measurements. The blue is salinity, the temperature is orange, and you might think, well, that's really small. But the temperature and salinity here is scaled as equal contributions to density. So where you see large changes in salinity, you see that it drives a response in density, which is the gray line. And please forgive me because I'm colorblind, so I get this wrong all the time. I think it's gray. And the contribution of the small temperature changes to density are really very small in the polar oceans. But there are a lot of wiggles in salinity here. Something is going on. The horizontal gradients that we're experiencing from such a simple measurement are very energetic. And this is thousands of kilometers, right? And we can scale down and we can zoom in to this little, just this little patch of data, and we can go to, 100-kilometer scale, and we still see these wiggles and changes in density in the surface layer, which is represented as sort of the mixed layer density. So something's going on here. There's a lot of lateral circulation at play, or variability at least. Now, what I did next was I took this time series and I sampled it at different resolutions. So it's actually got a 400-meter resolution, but I subsampled it at different resolutions, like 1 kilometer, 5 kilometers, all the way up to 50 kilometers, to see what do we measure comparatively with a ship or maybe a satellite measurement that has relatively low resolution compared to the 400-meter sailbuoy resolution. And what you get is this histogram, this drop-off in density gradients as a function of the length scale. So what it means is that here we calculated all those lateral gradients, how much the density changed as a function of distance. So kilograms per meter cube density as a function of per kilometer. And we plotted all those histograms at the finest scale, a few hundred meters, all the way to 20 kilometers. And the message here is that at the smallest scale, the gradients are the most energetic and frequent. So we have these large gradients per distance that drop off dramatically towards the mesoscale. So if we sample those at lower resolution, we don't actually capture these sort of submesoscale gradients. And here is the internal Rossby radius of deformation. This is the deformation radius that David introduced this morning, but only for the mixed layer, the average mixed layer there. And that's showing that we have these features that can occur at roughly a diameter of 2 kilometers in the mixed layer, because the mixed layer is very small, I mean, compared to the full depth of the ocean. So, give you some more sense of these scales of variability that we experience in the ocean. Now, maybe you are most familiar with the mesoscale. And here's the deformation radius from Shelton, where we can see that where we have this low Coriolis force towards the equator, we can grow these very large eddies that scale at roughly 100 kilometers. And as we go towards the poles and F becomes higher, we sort of can create these flows, these balanced flows that are in the order of around about 10 to 15 kilometers. So if we go at a scale below that, we get into the submesoscale. This is the 0 to 10 kilometer variability in the spatial scale, where the ocean is full of these vortices and fronts and filaments, etc. Now, these are really important, and sort of, I mean, what I'm trying to emphasize here, and by the end of today, is that these submesoscale features are important to ocean circulation, but of course to distribution of properties both laterally and vertically in the ocean. And it's really a subject of sort of current research. We're kind of just figuring out this, especially from observations. Okay, so these flows have very large vorticity. They have a large, strong curl and strong shear. And when you scale that to F, they are roughly in the order of 1 to 1. They scale approximately the same. And that means that F is starting to have less and less control on the balance of this flow. So the flow is becoming closer to unbalanced. And when this vorticity grows greater than F, these flows have large vorticity, they have large curl, and they become unstable. And they're not able to be balanced by the Coriolis force and stay upright and stay as a balanced flow. And so therefore they become unstable and decay and become eventually viscosity and turbulence in the ocean. They have small Rossby numbers, so compared to the mesoscale dynamics, they have small Rossby numbers, order 1, and they have small Richardson numbers of about order 1 compared to 1,000 for the full depth, large-scale mesoscale ocean. So let's have a look at how the first views of these submesoscales were known in real reality, not just from numerical simulations. And here we have this astronaut, Scully Power. He was, I think, on the International Space Station. And in 1986, he looked out the window when the space station was moving off the coast of Egypt. And he saw this eddy train here, this submesoscale eddy train, evolving in the Mediterranean Sea. And he took this photo, which really is sort of a function of the sunlight glint and particles on the surface ocean that created this image. And what you can see is that actually these eddies are scaling at about 8 to 12 kilometers, are really some of the first evidence from, that the ocean was varying at this fine scale outside of the numerical simulations. So that's a real nice way to think, okay, in the 80s was kind of the first view of these small vortices as viewed from space. In the Southern Ocean, they look something like this. And I went to go and trawl through the archive of, SAR imagery and found some of these images in the marginal ice zone. So here we have SAR imagery, which is roughly able to resolve things at hundreds of meters in resolution. And here you can see the Antarctic sea ice as that tracer again, like we spoke yesterday. It works as a wonderful tracer for the ocean circulation. And probably there is some shear in the current between the open ocean in the north and over the sea ice in the south that generates these submesoscale instabilities, almost in a way like the Kelvin-Helmholtz instabilities that we saw yesterday, being generated on the sea ice. And so these eddies are shown moving around the sea ice in these sort of circular patterns and vortices over the Southern Ocean. Okay, so right, so how do these submesoscales, how do they form and where do they get their energy? Well, I like to bring up our famous Table Mountain again, like yesterday, where yesterday we were talking about Table Mountain as being approximately the height of which we could see mixed layers change in the open ocean, especially the Southern Ocean, from this point to 5 kilometers away or 20 kilometers away, that the mixed layer may adjust by 1 to 3 to 400 meters over such short time and space scales. So now if you think of yourself as standing here, at the sort of base of Table Mountain and looking up, and now you're in the ocean, and this is the mixed layer, you can imagine that on this side we have this dense rock. Now, in terms of the ocean, this would be a dense side of a front, and you're sitting in the lighter side of a front, and you're looking up at this enormous mixed layer. And now you can imagine the available potential energy there is for this big front in the ocean, which has varying density from this side to the other side, to dissipate and become kinetic energy and become unstable and slump. And that is essentially one of the main ingredients for the submesoscale to form. It has a large potential energy because there are lateral gradients in the ocean, especially over these very deep mixed layers, which has this potential energy to be converted to kinetic energy, especially under unstable conditions when where the Coriolis force is too small to keep these balanced. And then the other aspect is strain. And like the image at the beginning, you see these submesoscale and mesoscale eddies interacting. And that is not just coincidence, but the strain, the squeezing and the stretching of these density fields from the mesoscale are providing the energy for the submesoscale to form. It is enhancing the rate in which these density gradients form over the ocean. Okay, so here is one way to kind of view this. Here's an idealized simulation from Belo Fox-Kemper. And what he has is a simple temperature front in an idealized view of the ocean. And of course, you can see that up to 200 meters here, there is no change in temperature, i.e. the change in temperature or density doesn't exist here, and this can be seen as our mixed layer. And what happens is if you start the simulation, you can see there, here we're running just several days. We can start to see that the long flow along this front here starts to become unstable. We're talking about very small scales, so we form these vortices, and eventually this very tall mixed layer, which has a change in density over it, starts to slump and want to lie. The warmer light water wants to lie on top of the denser cool water. And now we start to create, as those waters slump through these submesoscale eddies, we create new mixed layers that are much shallower than the conditions we had before. And this is what we term something called mixed layer eddies. Here's another view of it. Now, if you follow your eye basically just on the green isopycnal, so this is density, and if you follow this isopycnal in time, you can see how these instabilities form along the front and then start to slump and move this vertical buoyancy into a horizontal buoyancy, and we create the stratification in the form of these mixed layer eddies in these very fine scale simulations. We're talking about hundreds of meters of resolution over these models. Here it's a 250 meter grid size. Okay. Now, what was, I think, extremely useful for the community is that Boccoletti and Bailo-Fox-Kemper introduced a parameterization for mixed layer eddies. And I'm just introducing a relatively simple equation here by which we can quantify the effect of mixed layer eddies as an equivalent heat flux. And what I mean by that is that Q, think about this morning's lecture by Sarah, we see Q as a heat flux, you know, how much heat is actually put, watts per meter squared, into the ocean from, let's say, the sun. But an equivalent heat flux, it's equivalent because it's not an actual heat flux, can also be estimated by how much buoyancy these mixed layer eddies add to the ocean that can be then compared to the heat flux that you might measure from solar radiation, for example. And without going through all the terms, we have some constants here. We have F, heat capacity of seawater. But essentially, this term is varying as a function of the lateral buoyancy gradients, the strength of those density gradients, and H, the depth of the mixed layer. And if you have those measurements, you can quantify the equivalent heat flux that might be occurring from these mixed layer eddies to the upper ocean. All right, so these have maximal growth rates, which are usually theoretically constrained to the mixed layer. So they have a mixed layer deformation scale, which for, let's say, the mid-latitudes, where you have mixed layers of about 200 meters deep, they scale at roughly about 1 kilometer in the high latitudes. So think of the Southern Ocean as, in these mixed layers, these features can form at roughly 1 to 2 kilometers in scale. And what Baylor did then further was to take some satellite products, take some hydrography that we had available, and estimate where these heat fluxes, these equivalent heat fluxes from mixed layer eddies might be energized. Where are they mostly present? And so here we're flicking over the seasonal cycle, a monthly estimate, climatology, of where these mixed layer eddies are. And what might you notice? Why do we see these patterns? Would anyone hazard a guess? What drives these brighter patches of reds and greens where equivalent heat fluxes from mixed layer eddies are energized? Got to wake you up after lunch. Naomi. Mm-hmm, okay. Okay, so some ocean circulation. What is it about ocean circulation? What does it do to energize mixed layer eddies? Oh, come on, Anna. You can tell us. You're a Baylor student. Yeah. Okay, he answered everything for you. I'm sorry, Anna. Say it again.
Where you have strong lateral buoyancy gradients, like in boundary currents, or where you have deep.
Exactly. This pattern is a function of effectively only those two principles. Strong lateral buoyancy gradients, which you find at the edges of western boundary currents, and of course we have lovely strong lateral buoyancy gradients in the ACC, where we have these very large density gradients over space. David? Oh, let me start it again. Oh, you mean here? Why we blanked it out? Oh, well, I would hazard a guess. I actually haven't really thought about that. Damn you. Well, there's strong surface forcing here in buoyancy. We've got very strong warming, but we also have pretty strong trade winds, so that might add the surface forcing that we spoke about yesterday of buoyancy and wind might create these inhomogeneous view of the buoyancy gradient over the surface layer of the tropics. And then the mixed layer might be varying around that too, and it might then just be this good balance of high buoyancy gradients and deeper mixed layers as well. That's a guess. Does anyone else want to guess what's going on the equator?
Could the reduction in entropy play a role, like the actual stratification in gradients horizontally don't need to be as big to generate?
Yeah, low F. It could be. It could be. That's why Baylor here has removed most of the equator. No, it's gone. Yeah. So maybe there's something around the Pacific dynamics here, and that's, yeah, we should ask Baylor. Anna, can you ask Baylor? Okay, well, let's take us back to the Southern Ocean Summer School. And then, of course, the other aspect here was these deep mixed layers. So when these deep mixed layers are sort of coming together with these strong buoyancy gradients, we have these, which is you see in winter time. Then we have this large potential energy from which to form mixed layer eddies and re-stratify the ocean through mixed layer eddies. Okay, another Baylor plot here. Please don't tell Baylor that I'm showing all these images, because he might get a restraining order on me or something like that. But Baylor then added these mixed layer eddy parameterizations into models to see, well, who cares about these mixed layer eddies? They're so small. What does this mean really for the climate scale? And on the left here, we have a simulation where we can see the mixed layer depth with where mixed layer eddies and the equivalent heat flux from mixed layer eddies is not parameterized into the model. And what we see over the Southern Ocean is that we have these quite deep mixed layers. They're always in these orange and red, so 200 to 600 meter range. Then he reruns the simulation and he adds the equivalent heat fluxes from mixed layer eddies. So he's adding a buoyancy from mixed layer eddies into the model. And suddenly, first of all, we see a lot more gradients in the mixed layer itself, mixed layer depth, but also generally it's much shallower. So typically, numerical simulations have suffered from mixed layers that are too deep, but by adding these parameterizations, we can actually shallow the mixed layer to what we see more in reality. So that's just an example of when you do or don't have these mixed layer eddies included at the climate scale. Another example is this wonderful work done by S.Swart et al., where they had two simulations, one a 24th of a degree and a 48th of a degree, and they looked at the difference in vertical heat fluxes. Here we're looking at the vertical heat flux at the submesoscale. Now it's submesoscale because now we're only really resolving 10 to 30 kilometers. So is that, we're not actually into the submesoscale, but we're getting closer. And what you can see, in particular over the Southern Ocean, that the finer scale simulation where we could resolve finer scale features that were getting close to submesoscale generated much more vertical heat fluxes. And these vertical heat fluxes, bringing heat from below to the surface ocean, were also equivalent, would create an equivalent heat flux, so heat loss to the atmosphere from the ocean. So now we're looking at the air-sea heat exchange. And you can see that in parts of the Southern Ocean, these are 20 watts per meter squared. That's quite significant. That's missing from a simulation that doesn't include some of the fine scale circulation. This is a combined, this is not only a mixed layer parameterization, this is just resolving the ocean at a finer scale resolution. So the mixed layer eddies are doing something to suppress deep vertical mixing, but there are many aspects around the submesoscale which are increasing mixing and increasing ventilation with the interior. And I'm going to get to that in a few moments. But the other one is the wind-front interactions, vertical velocities from mixed layers. And mostly this pattern that we see here is a function of the submesoscale energizing W, the vertical velocities of properties up and down the water column. Yes, that's right. So these are instances where there are, when you increase the fine scale fronts and the strain, you increase W and you're able to bring up properties, let's say from the ocean interior just below the mixed layer into the mixed layer, and then resultant heat flux can occur. Okay, so how might these look from observations? We have these lovely model simulations where you have a perfect three-dimensional view at the fine scale. And now it's really difficult to think, okay, how do submesoscales, or how are they resolved in observations? And Sarah showed this morning some of the work done by Katie Adams and others, and JB was involved in this project called SMILES, where they found this wonderful cyclonic eddy, in the South Atlantic. It was in the Weddell Sea, just near Drake Passage somewhere. Oh, you can see by the longitude, didn't really check. And here we have this SST image from infrared, so we could get pretty high resolution SST, and there's this very nice strong front, and they went there with the ship and sampled it over this front to really look at how the submesoscale might be feeding off this mesoscale cyclone, where we have large strain and large buoyancy gradients in the lateral. And the one quick take-home message is that by looking at the vertical velocities as measured from the instruments on the ship, we could see that vertical velocities, which were at the mesoscale of kind of 1 to 10 meters a day, were being energized at more of hundreds of meters per day. So it's really a direct result also of the submesoscale energetics. And then we go to our gliders, of course, one of my favorite tools. And remember, the glider is changing its buoyancy and gliding through the ocean down to about 1,000 meters depth, measuring temperature and salinity. We have, like here, the CTD, and these dives are order 1 or 2 kilometers apart. So the gliders are measuring the ocean at very short spatial scales and temporal scales at the fine scale. And so we can try to use these gliders to estimate some of the submesoscale fluxes. And so some really nice work by Marcel Duplessis and his PhD at the time. We had been deploying gliders, for several years in this region of the subantarctic and subpolar Southern Ocean in this experiment called SOSEX, the Southern Ocean Seasonal Cycle Experiment. And one of the take-home messages here is that when you run one-dimensional models of what the mixed layer should do, and here we're looking at stratification, the 1D models, like a PWP model in this green line, differs from the observational stratification, especially in the springtime. So we have these big differences between the model, and then eventually they start to get more and more stable. Now we have a lot of solar heating, and the whole ocean stratifies in summer. But something is going on in spring that really can't explain the difference between what you would expect to happen from one-dimensional processes and what we actually measure from the gliders. And what these are responsible, what's causing these changes in having much shallower, sometimes mixed layers than the model, and sometimes deeper. Well, one of the main aspects, and I'm sorry, this is deliberately quite an energetic plot, which I'm going to get to, but if you focus only on the green lines, which is the mixed layer eddy parameterization estimated from the glider data, we can see that there's actual buoyancy being generated by mixed layer eddies way, way before solar radiation has taken grip and warmed the surface ocean and created all that buoyancy. Now, it's not only these mixed layer eddies that are important, but there is another process that I wanted to just introduce today around Ekman buoyancy flux. And that is that at the local scale, you have surface winds that are blowing over these fine scale fronts over the ocean. They're also the large scale ones, but let's just think at the local scale of the submesoscale fronts. And what happens is this schematic here by Eric DeSaro shows that if you blow winds along a front, you're going to generate an Ekman flow in one direction, depending in which hemisphere you are. And if you're blowing it along the front here and you have dense water in the southern hemisphere to the south, sorry, and you have lighter water in the north, like we do over the ACC, you can blow these dense waters over light waters and actually enhance the mixing through this Ekman buoyancy flux. And we can also quantify this as an equivalent heat flux. And this is simply as a function of the strength of the buoyancy gradient, how strong that front is, how strong the density gradient is over the front, and as a function of wind speed. So stronger you blow the wind and the more Ekman flow goes over the front, the more you can actually mix and bring this dense water over light water and actually enhance and mix the upper ocean. The other way is if you had to blow the wind up front, you would start to blow the light water over the dense water and you would actually enhance stratification. So Ekman buoyancy flux can be both positive and negative. So a restratifying or a destratifying flux to the upper ocean. Here we see this lovely simulation by Amala Mahadevan in the North Atlantic, in the study that was really set within the North Atlantic bloom experiment. And what you see here is we have a surface view of a density gradient. So here we have kilometers west and some distance. So it's really a surface view of the density gradient and front. And then here we have a cutout with depth of the same front. So here we can see these isopycnals near vertical in the mixed layer. And on the right, we have chlorophyll. So this model had a biogeochemical component of it, and we could estimate the chlorophyll as a response to the physics and the other aspects that are tuned within the model. And now if we run the model, what we see, similarly to those simulations by Baylor, Fox, Kemper, is that the front becomes unstable. It generates these mixed layer eddies. And nothing's really happening here because the mixed layers are still very deep because we are actually also blowing wind along this front to create Ekman buoyancy flux. As soon as we shut down the wind, the mixed layer eddies can start to dominate the picture because there's no destratifying flux from Ekman buoyancy flux. And we restratify the whole ocean, and the phytoplankton go crazy, happy to grow in the nice sunny upper reaches of the ocean. And the chlorophyll, you can see, blanks out to red here. So I'll play it one more time here. And what's quite critical is, of course, we're blowing a strong wind stress here for Ekman buoyancy flux, and as soon as that wind stress shuts down, we can see that the mixed layer eddies get very excited, and we can see the response in the upper ocean. The mixed layer shoals, and the phytoplankton starts to grow. So here we go, when the wind is shutting down. So we create all these mixed layer eddies, stratification is being enhanced, and the bloom occurs. Okay, so likewise, in the Southern Ocean from the gliders, the next part of Marcel's PhD was really to understand the impact of these Ekman buoyancy fluxes in the Southern Ocean. And what we saw from many years, starting in winter, so here we are in August, Southern Ocean winter, we have very low stratification, the mixed layer is deep. What you can see is that in time it stays deep, and then actually at some period in October, November, the stratification starts to grow, starts to increase. But it doesn't, every year it doesn't increase at the same time of the year. So in this case, the stratification started early, around 22nd of October. The next year it was in November. Another year it was late November, almost December, when the stratification started to increase. But if you looked at the solar radiation that was received at the same location, which is really fixed by the annual cycle of the sun, we could see that heat fluxes went above zero always in around October, and yet the ocean didn't stratify from the heat fluxes from the sun. So what's going on there? And this is really a remnant of Ekman buoyancy flux destratifying the ocean because the winds are blowing very strong. They are typically down front. The glider currents that are measured, these are like the ACC currents, are aligned very nicely with the wind stress, the nice westerlies that blow over the Southern Ocean. And so typically when we have colder, dense waters in the south, we're continuously blowing them over the light waters in the north and creating an Ekman buoyancy flux to mix the ocean. And so ultimately, this Ekman buoyancy flux and this mixed layer eddy are tangoing together. They're dancing together. They're positive and negative in the mixed layer, which results in this kind of interplay between these two submesoscale fluxes, the stratifying flux from the mixed layer eddy and the destratifying flux from Ekman buoyancy fluxes in the Southern Ocean, which is very unique. We have the wind and the current aligned in the same direction. Any questions for now? Okay. It's not always so easy. So you think, oh, we just put the gliders in and, we'll see them in a couple of months and just play on our phones and move them around. But then we have other things that are at play. And this is a nice example of, intense biofouling that some of the gliders experience, where they have these gooseneck barnacles growing here on the sailboy and here on the gliders. And it's anywhere that the boundary layer is moving away from the vehicle, is being disturbed by the vehicle, these gooseneck barnacles are happy to grow on the edges of the wings and behind sensors and cause havoc for us. And, sometimes we lose vehicles because of such biofouling. Okay, so I've spoken a little bit about the mixed layer physics that goes on, but what I wanted to briefly show you in just 2 slides was that these submesoscale circulations also have connections to the ocean interior. And this work done by Leah Siegelman, which was really nice, using some seal data from Kerguelen. This seal was going and diving, in this wonderful pattern. They managed to get a high resolution tag back, and they could really estimate these lateral buoyancy gradients very well from the seal as it was moving through the ocean. And so these are the colors you see. These lateral buoyancy gradients, red and blue, are when these density gradients are sharpest. So we have a potential energy that's applied from these lateral buoyancy gradients. Interestingly, these lateral buoyancy gradients, which are actually these black lines, kind of a function of it here, we've got a function of spice, lateral spice, are heightened over the standing meander in the Southern Ocean. So the big ACC is moving over the standing meander. There's some topography in the way. And just at the standing meander, or especially downstream, these buoyancy gradients get heightened. And then there's something called FPHT. And now I need to ask Sarah, first passage hunting time. Tell us, and now the seal likes this very much. So what's going on the ecology side of things? What is that metric? Do you know? Okay. So he's feeding. Okay, so the blue line is feeding, and of course the seal seems to really like this energetic part of the ocean. Something must be spurring on the ecology and whatever it's feeding on. And so she showed this nice relationship between these standing meanders, heightened buoyancy gradients, and seal feeding behavior. Now, these submesoscale gradients also really created some specifically high vertical velocities, and equivalently these vertical heat fluxes and heat transport. And you can see it here intermittently, sporadic through the ocean. So the submesoscale is not always uniform and happening, in the same way all over the place, but it has these heightened areas of energetics where maybe the mixed layer is deep, but in particular the lateral buoyancy gradients are sharp. Then some other recent work which I could point you to is the work of Lily Dove, and from gliders here again, she had mapped in density space spice on the top, and AOU, the apparent oxygen utilization. This is telling you how old water masses are as a function of their last time they were saturated at the atmosphere with oxygen. So low values here are very recently ventilated water. And they have this wonderful correlation between spice and AOU, which is showing that really these submesoscale filaments and features are creating ventilation pathways within the upper ocean. I mean, these are some of the first observations that kind of give us a good sense in the Southern Ocean that these connections exist. They are responsible for forms of ventilation. And then more recently, we're doing some work. Okay, we're on the northern boundary of the ACC here, and we haven't worked up this data properly yet, but we had some gliders, here in the Cape Basin, just south of Africa. And here's the raw oxygen data. And the same as Lily Dove sees. Okay, here we've got it plotted as a function of depth. But you see these wonderful filaments and features in the upper ocean, which are very, very fine scale. Here we're talking about 1 kilometer or 2 in space, and they're extending deep into the ocean. This is 1 kilometer depth data. So this will be very interesting data to a student is now working on this data to look at AOU and other patterns of ventilation that might come from these kind of measurements. Now, we can't really go without mentioning some of the satellite data. And what's been really exciting for the community is the SWAT data. Now, this is the SWAT altimetry that's provided from this new altimeter that was launched just last year, or a year and a half ago. And this figure here by a PhD student from Paris, Solange, working in Gothenburg at the moment, is really showing you one of these swaths of altimetry. You see the resolution of the swath altimetry as the small dots, and the other big dots are what we had before from the standard altimeter, NADAR altimeter tracks in a sort of gridded view. So now we can actually really look at the ocean in terms of sea surface height at a much, much finer scale resolution here. So we're able to resolve, getting closer to the 3 to 5 kilometer resolution in altimetry compared to the 25 kilometer. And just an example, so that during the FOST repeat phase, where the satellite was measuring this location every day early last year, here we are in the Cape Basin, and we put some gliders out here under the SWAT crossover region. This is just the broad view of it. But if you zoom into, just this little region over the Gullis retroflexion, what you might see from DUAX, the standard altimetry product, is the flow field looks like this on the surface from sea surface height. So we have some relatively smooth field of velocity. This is the edge of the Gullis current retroflecting, and it's like this quite smooth mesoscale view of the ocean. And what Solange has done is she started to process the SWAT data and actually have a look at the data along the SWAT swaths. And it's really very beautiful, because what we see is that the SWAT is now able to resolve submesoscale features. I mean, these are really very small eddies here that are found on the edge of the retroflexion. And you can see the same thing in the high resolution SST, which is roughly scaling at 2 kilometers or so. We see these two cooler eddies sort of pinched in the Gullis retroflexion as the color. And then we see the SSH contours from SWAT as these black lines really agreeing wonderfully well with the SST. So we have this really exciting phase now where we can use the SWAT data to resolve these features better in the global ocean. Okay, and so the last thing I want to talk about is something which Sarah was mentioning this morning, was about this coupling between the atmosphere and the ocean. So now we're going to the top boundary of the submesoscale and understanding how does this interact with the atmosphere. And this is really very difficult to observe. And this kind of image just kind of shows you a combination of all these processes in one space. We have the mesoscale. This is a false color image over near South Georgia, over the Southern Ocean. And you can see the phytoplankton blooms at the mesoscale. We can see these tiny submesoscale eddies and filaments here at the 1 to 10 kilometer scale. Then we have these huge atmospheric storms moving over the same area, interacting with this fine scale circulation at the 1,000 kilometers. And so this is really quite a complex pattern when you think of all of these processes interacting in one. And what our big challenge is, one of the major challenges within this sort of scale is how does the ocean and the atmosphere couple at the fine scale? how do these submesoscale features and filaments, which are very intense and have very strong SST gradients, how does that impact the atmosphere and air sea fluxes of heat and carbon, for example? So Sarah showed a different version of this one, but basically what we have on the top plot here is our observations of ocean temperature. Let's say it's from mostly filled out here by the Argo array and the SOCOM array, where both in winter for the last 10 years and in summer, we have wonderful coverage over the ocean and also over the Southern Ocean. Of course, there are still major gaps in the ice-covered regions and in the polar seas. But now when you try and think of how do we match those observations of the ocean, filled up pretty well from Argo, with those from air-sea fluxes. So variables that we need in the atmosphere to calculate an air-sea flux. So remember those calculations that Sarah showed you of the turbulent and sensible heat fluxes or the momentum flux? We have no observations, or very few. We've been so reliant on some ships going nearby or those two moorings that she mentioned, the OOI mooring and the SOFS mooring. So here we have a real big gap to try and close this big gap between the ocean observations and the lower marine boundary layer observations, which we hope that are going to be filled much more by technologies like USVs and drifters. I'm going to skip this for a time, but Sarah showed a different version of the same figure where we have big differences in the reanalysis products. How is the fine scale contributing to this uncertainty is something we really don't know. Okay, now how do those systems couple? Now, okay, this is a hell of a fast simulation. I always fear that someone's going to get Tourette syndrome or something from staring at this too long. But Marcel Duplessis made this lovely image over the Agulhas current, and we have all these eddies and anticyclones, which you see here from an algorithm which has determined where these eddies are. And you know that the Agulhas current flows down the east coast and retroflects and has a very strong temperature imprint on the sea surface. And then you throw the storms over it. So these are reanalysis Aero5 storm passages. You see the air pressure contours. And you throw those storms over the strong SST gradients, and what you actually see is the imprint of the ocean into the atmosphere. So this is the heat flux that's lost from the ocean to the atmosphere as a function of the ocean circulation. You can actually see the ocean eddies and boundaries, and this is only at the mesoscale. This is a 25-kilometer product. So we have a long, long way to go to start to resolve the smaller scale impacts on the atmosphere. We have some evidence, and this is really some lovely data from the Brazilian program where they have an eddy covariance tower on the front of their ships, and these are direct measurements of the flux of heat and carbon. Here I'm showing heat, so it's eddy covariance heat flux. And the message from these plots are that when you estimate these heat fluxes from bulk parameterizations, just from air temperature and let's say ocean temperature, and you compare them to the actual measurement from direct eddy covariance, there are huge differences. You're talking about differences that are often in the order of 100 watts per square meter. So there's a big problem here. Something is not working in the bulk formula, which we use for climate models and weather prediction. Broadly, they're not getting it right all the time. And this is largely a function of sea surface temperature gradients occurring at the fine scale. So small gradients that the eddy covariance, that the bulk formula don't really pick up in their algorithms are seen in the eddy covariance. And so we have really much work to do to try and improve these bulk formula to be sensitive for specific regions like the Southern Ocean where we have high wind and wave conditions. Okay, so that's it. I just highlighted a few challenges. The main one I've spoken about is that what we really need is much more observations and modeling activities where we have direct atmosphere-ocean coupling occurring within those simulations and observations. So on the observational side, we need better observations of dissipation, as I showed yesterday, and we need coupled platforms that are measuring the surface boundary layer and the fine-scale ocean of the upper ocean together. We have this big gap in the autumn, winter, spring months, as we all know about. And then, of course, the sea ice is a big challenge for technology to get more observations. Of course, see a little bit more of Channing's poster, but you know, the seals are doing a lot of work here, but they're not coupling to the atmosphere, and we don't have a good sense of the ice-ocean atmosphere fluxes and interactions. And that's where I'll leave it. Thank you.